Take it away, Shannon.
Thank you, Rebecca. So our task ultimately is to figure out what sort of molecules are present in the atmosphere of an exoplanet. This is a non-trivial task for lots of reasons. And one way to imagine how difficult this task is just to go outside at night and look at a star. Take any star you want, look at it and notice that it's an incredibly small area in the night sky. Of course, we're going to use telescopes, and we have some really, really powerful telescopes that we can use to see the stars, but seeing the planets is even harder. And so we use some typically indirect methods to determine the presence of those planets in the first place. And then we also use these similar indirect methods to determine the presence of an atmosphere, and then to determine specifically the composition of the atmospheric ingredients in whatever planet we're trying to look at. Next slide, please, Rebecca. So in order to complete this particular activity, your students need to be familiar with the basic ideas behind spectroscopy, which we'll talk about a bit today. So the idea that each element gives off a unique set of wavelengths if it is heated. Similarly, it will absorb or take in those exact same wavelengths of light if it is cool and a rainbow of light is passing through it. Your students need to be familiar with the basics of stellar evolution. So hopefully they have been introduced to the HR diagram, which plots luminosity versus spectral class or temperature. And they have a basic understanding of main sequence stars, white dwarfs, red giants, things like that. They may or may not be familiar with the other types of stars, including like variable stars and supergiants. That is of less importance for this particular topic. Stellar classification. So as I just mentioned, the x-axis of the HR are Hertzsprung-Russell diagram. So if they understand that stars are classified based on temperature, the reason stars are classified based on temperature is because basically all stars are made more or less out of hydrogen. Yes, of course, there are some other materials in there, especially younger stars such as the sun, for example, but the job of stars is to fuse hydrogen into helium. Hence, that is their primary ingredient. And so that's not a good way to classify them. A better way to classify them is based on temperature. Lucky for us, and those of us that can see all of the colors of the spectrum, we can just go outside and look at the color of a star. And from that, we are able to judge its spectral class or its temperature. Your students should also be familiar with the basics of Blackbody diagrams. So the idea that something or things that behave like black bodies, specifically something that's hot enough to glow, will give off light proportional to what its temperature is. When I'm teaching this idea in my class, what I do is I reference things that we are already familiar with. So students may have a electric stove in their house, and when that element gets hot enough, it actually glows a kind of a dull orangish red hue. Or coals in a fire. So here in Montana, we go camping. Of course, right now we're not having any campfires because the forest is on fire, but generally speaking, so if there are coals in the fire, those are hot enough to glow as well. So stars are another great example of things that behave like black bodies, but I like to bring it home and remind my students that they, even though the term black body radiation is a little bit intimidating and maybe sounds sort of weird, they almost certainly have interacted, at least visually, with things that behave like black bodies. Finally, our students need to be familiar with a couple, or at least one method for determining the presence of extrasolar planets or exoplanets. I talked to them, as I mentioned in the introduction, this idea that we can't see these planets directly almost ever. There are very, very tiny few examples of direct imaging of planets around other stars, but they're just so far away. They're so tiny compared to their stars, and they're so incredibly dim that we have to use indirect methods. I take a historic approach, which I enjoy doing, generally speaking, with astronomy, but specifically with exoplanet detection. I start with the Doppler method, since it was discovered first, and then move forward to the transit method. So we'll touch on each of these, and then we'll put it all together, and we'll think about how we can actually determine the composition of the atmosphere of an exoplanet. Next slide, please, Rebecca. Thank you. So we'll start with the transit method. So what we can see here is the idea that sometimes a planet will transit or go in front of a star. Now, something that I think my students tend to struggle with, and I'm not totally sure why, but it's the idea that other planetary systems are oriented randomly with respect to us in space. There's no reason to think that, even though the galaxy, generally speaking, is a flat disk, that doesn't mean that all planetary systems are lined up with respect to ours in the same plane. So first, I teach the idea that they are all randomly oriented with respect to our solar plane. And what that means is that we're not going to be able to use the transit method on every type of, or on every various orientations. So assuming that with this particular orientation, we have a star, and that star has a planet that happens to pass in front of that star with respect to us, that allows us to apply or use the transit method. And what that means is that we are undercounting the total number of exoplanets in our galaxy, because if a planet happens to be rotating like this with respect to us, then it's never going to transit or pass in front of that star. So this will give us a minimum count of exoplanets within our own galaxy. So assuming that we do have this particular orientation where the planet moves in front of the star, what that means is that when the planet transits or moves across the star, the total amount of starlight is going to decrease, and it's going to decrease by just a little bit. One note about this method requires a star to be giving off a nice steady amount of light. Specifically, what we're going to be looking at is preferably main sequence stars. The other reason we want to be looking around main sequence stars is because those are the stars that are in the best part of their life. That's when they're fusing hydrogen into helium. They are very, very steady. They don't tend to change size a whole bunch or vary in terms too much about how much material they're spewing off into space. And so we're looking for those nice, steady main sequence stars. Also, we're looking for stars that aren't super, super hot. So we're not typically going to look for exoplanets around type O or type B stars, the very hot, super, super blue stars, because they're giving off large amounts of ultraviolet light. They may very well have exoplanets around them, but they're significantly less likely to have life around them because those stars are so incredibly hot. So given those caveats, what we're going to do is we're just going to wait. And the Kepler mission is a great example of a telescope that was looking at many, many, many thousands of stars all at the same time, just waiting, basically looking and seeing that that star was giving off a steady amount of light. And then this teeny, teeny pinpoint of a planet goes around or moves in front of that star, so comes between us and that star, and that total amount of starlight dims by far, far less than 1% of the total light. It's incredibly tiny, this change in total light being given off. But this planet really does just act basically like this black disk, blocking out that tiny bit of starlight that is directly behind it. Even though this is a really, really small percentage of the total light or change in the total light, we can glean some really, really interesting information from this. So if we look at these two cartoons here, and they are linked up with each other time-wise, we can see that in position 1, the planet has not begun the transit yet. Position 2, here's the really interesting spot. This is when it is partially covering the portion of the sun that it's going to fully cover. At position 3, that's when there's the maximal dip in the total amount of light being given off. And then it doesn't show 4 and 5, but we could imagine that it continues, it exits on the other side of the star, much as it entered in position 2, and then goes around back behind the star. And it's of course going to do this in a very regular fashion according to Kepler's third law. I have an example from here on Earth. The next slide, please, Rebecca. I love this picture because I don't know if y'all were around for this or not, but Venus transited or went in front of the sun twice during our lifetimes, once in 2004, once in 2012. This is not going to happen again within our lifetimes. The amount of time it takes for this to happen, it happens within two quick time periods, about every 600 years or something like that. So if you didn't catch it back in 2012, unfortunately, we're not going to have this opportunity within our lifetimes. But the reason I wanted to show you this is because we can see here, this is the best possible picture we're going to get of a transit. So we've got our own sun, and so it makes up, a relatively large disk. And then also Venus makes up a relatively large disk as well. And so we must bear in mind that as labeled here, these are two separate time periods, right? So pretend like maybe the 2004 one isn't there. You can imagine that if you were not aware on this day in 2012 that Venus was transiting the sun, there's no way you would notice this, right? Because the disk of Venus is so tiny compared to the sun itself, you're not going to notice this itsy bitsy dimming of the sun. But this is way, way, way better resolution than we're going to get from any exoplanet at all. Next slide, please, Rebecca. So back to this idea. So we're thinking about this. So this is sort of a gross misrepresentation in the top picture, in that it looked sort of similar to Venus transiting the sun, right? So we're not going to get nearly this type of differentiation between the size of the sun and the disk of the planet moving in front of it. This is a very difficult task, and lucky for us, the computer software these days is good enough to actually use that information there at position 2 to help us figure out the atmosphere of the planet, and that's what we want to focus on eventually. Next slide, please, Rebecca. So blackbody radiation is the idea that hot things glow, basically. Go ahead and click that link there. We'll see if this FET will pull up. I really like this FET. I don't know if y'all are familiar with the CU Boulder FETs or not, but these are some wonderful, wonderful tools. They are, in this case, slightly interactive, but interactive enough that it's actually really, really a very neat way to show what the idea of blackbody radiation is. So what we're seeing on the y-axis is the spectral power density. I just tell my students who are not particularly math savvy, nor it's unclear their dedication to the love of units. And so I just tell them it's the total amount of light being given off by this particular blackbody. What we're seeing on the x-axis is the wavelength. And Rebecca, if you play with that blue triangle, yep, that one right there, and just play with that a little bit, we can see that not surprisingly, two things are varying here. The first thing that's varying is that as the temperature goes down, the total light output decreases, and the peak wavelength shifts as well. So something that's cooler but hot enough to glow still, like that electric stove element that I mentioned a little bit ago, that is relatively cool. I mean, you certainly don't want to touch it, right? But it's cool enough that it will glow a mere red, and it doesn't give off a whole bunch of light. It's not like it glows super bright or anything. And as the temperature increases, both more light is being given off, as is demonstrated by the fact that the peak is increasing, right? The area under the curve is getting larger, and that the temperature, or excuse me, the color at which it glows, or the color at which we see it, changes as well. It moves towards the blue. So type O stars, for example, are giving off a decent amount of ultraviolet light, but the way we can't see ultraviolet, right? Because it's too purple for our eyeballs to see. Nonetheless, they will look blue to us in the night sky. So a great example of a blue star would be, actually, there's an entire cluster. The Pleiades is a wonderful, wonderful example in the winter night sky of hot blue stars. If we go to the other end and think about cooler red stars, a great example of that, or my favorite example, would be Betelgeuse. Betelgeuse is one of the shoulders in Orion, so also happened to be a winter example. So generally speaking, stars are creating all the colors of the rainbow, actually creating more or less the entire electromagnetic spectrum, so all the way from gamma rays to radio waves in the interior of the star. So that fusion process is just creating energy, it's creating light, it's creating helium, of course, and so stars behave like black bodies in that they're giving off every color of the rainbow. But that the stars, generally speaking, have atmospheres, and the sun is, I could be wrong about this, but I think probably the sun's atmosphere is the best studied atmosphere of any star, generally speaking. Maybe not, I take that back. But we know what the sun's atmosphere is like, and the reason we know what the sun's atmosphere is like is because given that the sun behaves like a black body and all the colors of the rainbow are being created on the interior, the atmosphere of the sun is cooler, and it is going to absorb, based on what element or molecules are present, it will absorb certain wavelengths. Rebecca, please return to the slideshow, and we'll go to the next slide. Thank you. So here we can see and emission spectra for various elements. And these are elements, at least some of them are relatively common in stars. And so what we see is that using some pretty basic quantum mechanics, we can figure out which element is going to give off, or for each element, what specific spectral lines are going to be produced. In other words, if we take pure hydrogen and we heat it up hot enough so that it glows, it looks a certain color to the naked eye. But if we take that light and we carefully separate it out by wavelength using a really nice prism, or more ideally a diffraction grating, what's going to happen is that we're going to actually see that it's just giving off very, very specific discrete wavelengths as a direct result of the fact that the electron energy levels are quantized. So we take that exact same material, so let's stick with hydrogen for now. If instead it's cool and there's a light bulb behind it, and that light is going through that cool hydrogen, those exact same wavelengths will instead be absorbed. So again, as a direct result of quantization. Okay, so a star behaves like a black body. It's giving off it's creating in its interior all the colors of the rainbow. In the star's atmosphere, certain molecules and elements are present, and they absorb some of those lines. Now, what about the planetary part? Next slide, please. So what we really want to do, of course, is we want to figure out as much as we possibly can about exoplanets. And we have to use indirect methods because, as I mentioned, we can't really directly photograph them. In the very rare occasion we can. Nonetheless, that isn't going to help us a whole bunch with respect to that planetary atmosphere. And if we can have some sort of understanding of planetary atmospheres, that can really, really help us understand what's happening at the surface of that planet. And so here I have an example of the absorption spectra, and this is from the lecture tutorial, actually. This is the absorption spectrum of Earth's atmosphere, something that we can certainly measure. And so on the y-axis, we've got something similar to what we saw with that black body curve. And on the x-axis, we have the same thing again. So we've got intensity or irradiance versus wavelength. And what we can see is that because we can just do some quick quantum mechanical calculations, we can figure out what molecules are present in the Earth's atmosphere because we know what wavelengths they will absorb. And so we can see the water lines, for example, the oxygen lines, the ozone lines. And this is really, really, really powerful. It's much easier to use, of course, within our own solar system because everything is just so much closer. Nonetheless, putting this all together using the transit method, we can take advantage of the fact that the sun, that star is giving off starlight in a constant fashion, right? So it's not really changing how much or what colors of starlight it's giving off with respect to time. As that planet is heading towards the transit, as it is just grazing the edge of that star, then some of that light actually shines through that that planet's atmosphere, gets absorbed based on the molecules and or elements that are present in that atmosphere. And we can use that tiny bit of data to try and figure out, we subtract out the star and figure out what the atmospheric composition is more or less for that particular planet. And that is our task for today. That's all I have for this mini lecture. I'm more than happy to take questions, or we can move on to the breakout rooms.